Hello and welcome to the Theory of Computation lectures. In this class, we will introduce ourselves to Deterministic Finite Automaton. Now here is an example of a DFA, which is an abstract machine and is denoted by a 5-tuple given by Q sigma, Q0, F and delta. A DFA consists of a finite non-empty set of states given by Q. So in this figure, A, B and C are the three states. Okay. So a state is a representation of memory. For example, suppose the machine is currently in state B. So if I ask you, can you tell me what was the last input? Would you be able to answer that question? The answer is yes. You will tell me the last input was 0. Okay? Because if the machine is in state B and there is only one way to enter state B, we can come to state B from state A via this transition, and this transition happens when the input given to the machine is 0. Okay, so when the machine is in a state, we can tell what was the previous input, right? So based on that, we can think of a state as a representation of a memory. So in this machine, there are three states given by A, B and C. Then we have a finite non-empty set of input alphabet, which is represented by sigma. So for this machine, we have two input alphabets, 0 and 1. So if you look at every edge, apart from the initial edge, every edge is associated with a symbol or an input alphabet, and which could be either 0 or 1. So in this example, sigma is a set of two symbols, 0 and 1. Then we have an initial state, we call it Q0. Now state A is the initial state. This is represented by an incoming arrow without any input alphabet over it. So in this machine, the initial state Q0 is A. Then we have a set of final states. For this machine, there is only one final state, C. This is understood by a state where there are two concentric circles. So for this machine, the set of final states consists of only one state, which is C. But there can be more than one final states, as we will see shortly. Then we have a transition function delta, which tells us, given a current state and the input, to which state this machine should go to. For example, in this machine, the transition function delta can be represented by this table. Here are the states A, B and C, and here are the input symbols 0 and 1. So what this table tells us is that if the machine is in state A and it receives an input 0, it will go to state B. So if you look at the corresponding figure also, you see the same thing. If the machine is in state A and it receives input 0, it goes to state B. Similarly, if the machine is in state A and it receives input 1, it goes to state C. So from A, if we receive input 1, we go to state C, and so on. So basically, a state transition table is a representation of the transition function delta. Okay, and also this diagram, which is called the state transition diagram, can be thought of as a representation of the transition function delta. Now, one interesting question is, how many final states can be there in a DFA? Well, first of all, we saw this machine where there was only one final state given by state C. But is it required that a machine must have a final state? The answer is no. So there can be a machine where there are no final state. As you can see in this machine, there are no final states. So the set F is basically the empty set, phi. So it is possible that a machine does not have any final state. Now what is the meaning of a final state? The final state is a state in which a machine accepts a given string. So if the machine does not have a final state, that means this machine will not accept any string, right? It is possible for a machine not to accept any string. It's theoretical possibility. So F equal to phi is possible. Then it is possible also for the machine to have all its states as final states. So in this machine, there are three states A, B, C, and all of them are final state, which means that the machine will accept all possible strings constituted from the input alphabet or a universal set of strings. So the size of the set of final states can be at least 0 or at most the number of states in the deterministic finite automaton. So now let's talk about the characteristics of a deterministic finite automaton, or specifically we want to talk about why is this machine called a deterministic and a finite machine? Let's talk about finiteness first. So we have already discussed that the concept of a state is a representation of a memory. Whenever we want the machine to remember something, we change the state of the machine. And number of such states is finite in this kind of a machine. That's why we call it a finite automata. Now, why do we call it a deterministic machine? So let's try to understand what the term deterministic means. Basically, when we say the machine is deterministic, that means there is a way for me to predict what will be the future behavior given the current state and the input. For example, think of your fan. Suppose the fan is rotating right now. Now, if you switch off, then can you tell me what will be the state of the fan? Well, if I switch off, the fan will of course stop rotating, right? So we can predict what will happen to the fan looking at the current state of the fan and the input that I am going to give, or the command that I am going to give. So that kind of a behavior is called deterministic behavior, when we can predict the future state of the machine looking at the current state and the input. Now, deterministic has two connotations. The first one is, from any given state there can be only one transition per input symbol. For example, if you look at this machine, now suppose the machine is in state A. So if the input alphabet has only two symbols, 0 and 1, if I give input 0, then it goes to state B. And if I give input 1 from state A, it goes to state C. But if you look at this machine, now from state A on input 0, it can go to state B or it can go to state C as well. So if I ask you, in this machine, suppose the machine is currently in state A and the input given is 0. Can you tell me which state it will go to? You will not be able to answer, right? Because it can go to either state B or state C. So there is no way to determine which state exactly this machine will go to depending on the current state and the input. So this is a non-deterministic behavior, and this machine is not a DFA. Whereas this machine is a DFA because from a current state given an input, we can tell exactly which state it will go to. The second thing is that there must be a transition for every input symbol from any given state. So for example, if you look at this machine, suppose we are in state A. So there are two possible input symbols, 0 and 1. Now, is there a transition for both these input symbols? The answer is yes. From state A, if I give an input symbol 0, it goes to state B. From state A, if I give an input symbol 1, it goes to state C. Again, from state B, there are transitions per input symbol. For example, from state B, if I give an input of 1, it remains in state B. If in state B, if I give input 0, the machine still remains in state B. So that means whether we give 1 or 0, the machine will remain in state B if the previous state was state B. Similarly for state C. So this machine is a deterministic machine because there is a transition for every input symbol for any given state. But if you look at this machine, now from state A, if we give an input symbol 0, it goes to state B. If I ask you, what will be the next state if I give an input symbol 1 in state A? Now, can you answer that question? There is no depiction of that in this machine. So we don't know what will happen if the machine is currently in state A and the next input symbol is 1. Hence, this behavior is non-deterministic. Whereas in this machine, the behavior is deterministic. So I hope we have understood what is a DFA, what are the 5 tuples that constitute it, and why do we call it a deterministic and a finite machine. In the next class, we'll do some problems with DFA. Thank you.